Hi, folks. I've already hinted at this about sodium being reactive because it doesn't have a full valence shell. Fluorine is also very reactive because it doesn't have a full valence shell, but it's really, really close. It has 7 valence electrons. It just needs one more electron to have a full valence shell. So, as I said earlier, atoms are more stable with a full valence shell, like the noble gases. And for the most part, what makes a good, stable valence shell is having 8 valence electrons, the octet rule. The exception to this are the smallest atoms and ions. That first energy level can only hold 2 electrons, and so 2 is considered full for those smallest atoms. The very smallest atom, hydrogen, is actually also stable with 0 electrons, or somewhat stable. So an empty outer shell is approximately as stable as a full one. And I'll show you on the next slide kind of how that works. But sometimes atoms are going to gain electrons to get a full valence shell, but sometimes atoms are going to lose electrons to get a full valence shell. And it's just whichever one is more energetically stable or takes less energy to bring about, that is the one that's going to happen. So atoms can get a full outer shell by gaining electrons or losing electrons. That process forms ions, which are atoms with a charge, remember. Or by sharing electrons. This is when they make covalent bonds, and that's something we're going to learn more about in Module 4. Right now we're going to focus on the ion strategy. So an ion is an atom or molecule with a charge, and there are 2 types of ions. There are cations, which are ions with a positive charge, and that happens when an atom loses electrons. Typically, the kinds of elements that lose electrons are usually metals. Metals tend to form positive ions. And when we refer to sodium, positive ions, the name doesn't change. So for instance, Na is a sodium atom, and Na with a positive charge is going to be a sodium ion. We call them both sodium. This is why, the naming is a little bit unfortunate, but this is why people get confused about sodium and are surprised to hear that sodium is a metal. Sodium, the element, is a metal. It's shiny, it's silvery, it's an unusual metal because you can cut it with a butter knife and it releases a flammable gas when it reacts with water, and so it catches on fire. Sodium ions are what you are used to in terms of the sodium chloride that's in salt that you sprinkle on your food. Those ions with the different name, even the ions have the same name, but they're a different substance. Obviously, the salt you sprinkle on your food is not a shiny, silvery metal. So people struggle similarly with potassium. They think of potassium as being in bananas. That's not a metal. But potassium is a metal. It's just a very, very reactive metal. So you're used to seeing the ions and you're not used to seeing the metal. The other type of ion is an anion, a negatively charged ion. And anions form when an atom gains electrons, because electrons have a negative charge, so having more of them causes the atom to be negative. It's typically nonmetals that form anions. So oxygen, fluorine, chlorine, those elements form negative ions. They tend to gain electrons. But for the anions, we do change the name when we're talking about it. So we don't talk about oxygen ions, we call them oxide ions. Nitrogen is called nitride, chlorine is called chloride. So we're consistently changing the ending to IDE. It's important to keep straight what's a cation, what's an anion, and my helpful memory device to help you remember what a cation is cations, like cats. You know, the ones that say meow. Cations are positive. because cats have paws. So if you don't want to hear me say that stupid pun in class, then please remember that cations are positive and anions are negative. If you remember it, I don't have to repeat it. So an atom is going to tend to form the ion that gives it a full outer shell and moves the fewest electrons. Because the more electrons you move, the more energy it takes. And this is all about making stable atoms, like low energy atoms. The way you calculate charge, because protons are positive and electrons are negative, then you calculate the charge by doing the protons minus the electrons. And sometimes students get confused about this, so I sometimes relate it to sports scores. Like if I've got a tie game, it's because the protons and the electrons were equal. Okay, when protons and electrons are equal, the overall charge is 0. If you've gained 2 electrons, that's like the electrons winning by 2. And because electrons are negative, it means that the overall charge is -2. If you end up with the protons winning, if you're losing 3 electrons, for instance, that means the protons won. And protons are positive, so winning by 3 for the protons means the overall charge is +3. So sometimes think of this sports analogy helps people figure it out. Or you could always, so it's, you don't strictly speaking have to go to the periodic table to find out how many protons there are to begin with. You can just do it based off of the change in electrons, figuring out what the charge is. So let's do an example and see how we can predict what kind of charge forms with an element like aluminum. Aluminum has 13 electrons, so my Bohr model would have 2 electrons and 8 and then 3 in the outer shell. And so there are 2 different ways I can get a full octet here. I can gain 5 electrons to get up to 8 valence electrons, right? We're trying to get a full octet. The way to get 8 is to add 5. If I add 5 electrons, then the electrons are winning by 5. That means that overall, this atom has a charge of -5. So I better put a charge on it to indicate that this isn't an atom anymore, it is an ion. Alternatively, instead of gaining 5 electrons, we could lose 3 electrons. Those 3 electrons that are in the outer shell, we could just cross them off, make them disappear. In this case, we lost 3 electrons. So the protons are winning here, and we have a charge of +3. So I've just made kind of 2 arguments here. One is that aluminum could make ions with a charge of -5, or aluminum could make ions with a charge of +3. In reality, only one of these ions forms. The ion is going to form the one that requires less energy to form, and that's going to be the one that moves the fewer electrons. So this second ion is the one that actually forms, and aluminum always forms ions with a charge of +3. So I want you to pause the video and do a few practice problems to kind of think through it the way we just did with aluminum. So boron, like aluminum, has 3 valence electrons, so it could lose 3 electrons or gain 5 electrons. Which one's more likely to happen? The one that moves fewer electrons. So you're more likely to lose 3 electrons, which means protons win, and the ion is going to be boron with a charge of +3. Oxygen has 6 valence electrons. It could lose all 6 of those, or it could gain 2 electrons to get up to 8. Which one's more likely to happen? It's more likely to gain those 2 electrons to make an ion, an oxide ion, with a charge of -2. Sulfur has 6 valence electrons, so it could lose 6 or gain 2 electrons, and it's more likely out of the 2 of those to gain 2 electrons because that moves fewer electrons, and that makes an ion with a charge of -2, the sulfide ion. I hope you're noticing a pattern here about elements in the same group. And if 2 atoms have the same number of valence electrons, they're going to tend to form ions with the same charge. Now, one thing to note is that those ion charges that we just came up with for metals, except for groups 1 and 2, most metals are multivalent, and that means that they can have ions with different charges. The notable exceptions for this are scandium, which is always +3, zinc, which is always +2, silver is +1, cadmium is +2, and aluminum is +3. Please do not rely on the pattern that we just did for other metal ions. So especially things like tin can be +2 or +4. Same thing for lead, and kind of all of the metals, most of the metals in the dip of the periodic table. Please also remember that all atoms have a charge of 0. What we're talking about here is the trend that we're learning here is helping us predict the charge if an atom becomes an ion. Elements always have 0 charge, but we're predicting what ion these elements would form in their compounds. So since the common ion charge is tied to the number of valence electrons, we can reason out what the ion charges are as based off of the number of valence electrons. So in group 1, those have 1 valence electron. Are they more likely to lose the 1 valence electron or to gain 7? They're more likely to lose 1, giving them a charge of +1. That's why these alkali metals are so reactive. They only have to lose 1 electron to get a full valence shell, and that happens extremely readily. In group 2, with 2 valence electrons, you're more likely to lose 2 electrons than gain 6. These are reactive metals, but not as reactive as group 1 because you need to move 2 electrons to get them a full valence shell. We're skipping the dip here and moving to group 13, which have 3 valence electrons like aluminum and boron, which we already did, so a likely charge of +3. Group 14 is a bit of a odd one. You can kind of label it as positive or -4. If you've got 4 valence electrons, it's equally easy to gain 4 or lose 4 electrons. Now, it's not common to have an ion with a charge of positive or -4. This is more likely to be an oxidation number, and oxidation numbers are related to ion charges. In group 15, you're more likely to gain 3 electrons than lose 5. In group 16, you're more likely to gain 2 electrons than lose 6. In group 17, you're more likely to gain 1 electron than lose 7. And once again, these I mentioned that these were very reactive nonmetals because, again, they're like the alkali metals. They're just 1 away from a full valence shell, but on this end of the periodic table, you just need to gain 1 electron for a full valence shell. If you're in group 18, you already have a full valence shell. You don't need to gain or lose electrons for a full octet. So those don't form ions generally at all. So as I said, ion charges and oxidation numbers determine how elements bond. And it's important to realize, and I did circle them here, it's important to realize that these ion charges really only apply to the nonmetals on the right side of the periodic table. On the left side, groups 1 and 2 have predictable valence electrons and ion charges, but don't rely on these ion charges for the metals on the right side of the periodic table, because they are multivalent and can have more than one ion charge. I hope this helped.